Hello, am I audible?
Yes, sir.
Okay. Do you have any doubt from last class to any one of you?
No, sir.
Sir,
Yes.
I think I have read from Newton's law of cooling. So there is a T naught and then T initial and T final. I don't know. I don't get what is T naught. What's the difference between T naught and T initial?
Just 1 minute. Suppose a body which having temperature T at any instant is kept in surrounding of temperature T naught. So T naught is temperature of surrounding and T is temperature of that object. So its temperature may change from initial value Ti to some final value Tf. Okay. So
Got it,
Ti
sir.
and Tf is the change for that duration, and T naught is temperature of surrounding.
Understood, sir.
Any more doubt?
Sir,
Yes.
can you scroll from the heading thermodynamics?
Oh, just 1 minute. Do you have to take a screenshot?
No, sir, because I think I missed something. Yes, sir.
Okay. I will take your Viva at the end of the class. Okay.
Okay, sir.
Next is gas. We mainly have two different types of gas. First is called real gas, and second is called ideal gas. So what is the main difference between ideal gas and real gas? If in chemistry, if you have learned this particular chapter, thermodynamics, you'll be told the gas which obeys ideal gas equation, that is PV is equals to nRT, those gases are called ideal gas. But there is some insufficient information by this definition. So let me define you what is the actual difference between real gas and ideal gas. Suppose in a particular gas, if there is some interaction between particle of gas, if there is interaction between particle of gas, so due to this interaction, it will have some potential energy due to interaction, and due to its temperature, it will have some kinetic energy. So on adding these two energy for gas, it will be termed as internal energy. So internal energy is sum of kinetic energy and potential energy. Now suppose for a gas, if there is no interaction between particles, if there is no interaction between particle of gas, then in this case, potential energy will be zero since there is no any interaction between them, and kinetic energy will be due to temperature. So on adding these two terms to get internal energy, U will be equals to only kinetic energy due to temperature. So the gas which having internal energy in the form of kinetic energy as well as potential energy is termed as real gas, and the gas which having internal energy in the form of only temperature or due to kinetic energy will be termed as ideal gas. Is it clear?
Yes,
Yes,
sir.
sir.
Now, what will be the basic condition under which real gas will tend to behave as ideal gas? So let me define you. Suppose in a vessel, and let's say it is gravity-free space, enclosed and having piston. There is particle at this point, this point, this point, and this point. So what will happen if you compress this particular piston slightly downward? Will the separation between particle increases or decreases?
Decreases, sir.
So on decreasing separation between particle, force of attraction between them increases or decreases?
Increases.
Good. So if you have to decrease the interaction between particle, you must have to increase the separation between them. Is it clear?
Yes, sir.
Yes, sir.
So to increase the separation, we must have to increase this piston outward, or we must have to decrease its pressure or decrease the pressure of system. Is it clear?
Yes, sir.
So on decreasing pressure, separation between particle increases. So interaction between particle decreases. We can say. Raza, is it clear?
Yes, sir.
Okay. Next is, suppose we increase the temperature of that particular system. So it will acquire some thermal kinetic energy. And due to thermal kinetic energy, it will tend to vibrate randomly in all different directions. It means its kinetic energy increases, or its kinetic energy due to temperature, that is thermal kinetic energy increases. So again, we can say potential energy in that case will also decreases. So on combining these two statements, you can say on decreasing pressure and increasing temperature, interaction between particle decreases, or it will tend to acquire more thermal kinetic energy. So it will tend to behave as ideal gas. Is it clear?
Yes, sir.
So,
So you will be asked, under what condition a real gas will tend to behave as ideal gas? So you will say at low pressure, why pressure should be low? So that to increase the separation between particle, and at high temperature, why temperature should be high? So that it will have more thermal kinetic energy. At these two conditions, real gas will tend to behave as ideal gas. Nabila, is it clear?
Yes, sir.
Okay. So we can say at low pressure and high temperature, real gas will tend to behave as ideal gas. Okay, just write it down. You all have done?
Yes, sir. Done.
Minashi, any doubt?
No, sir.
Okay, next is zeroth law. Since it is defined after first law and there is no any natural number before 1, so it is termed as 0. This particular law simply defines you concept of temperature. So if you will be asked which thermodynamical law will define the concept of temperature, so you'll say zeroth law. Suppose you have system this wall is adiabatic, which restricts any exchange of heat through it, which restricts any exchange of heat. This is diathermal wall, which allows heat exchange. Now let's say this is system A, this is system B, and this is system C. Individually, all are at different temperature. So since this particular wall is diathermal wall, so across it, there will be some exchange of heat due to their temperature difference. So you'll say A and C will interact with one another and there will be flow of heat between them till they acquire equal temperature. Similarly, in case of B and C as well, there will be flow of heat between these two systems till they acquire equal temperature. So at equilibrium, since this particular system is in thermal equilibrium with this part, and this is also is in thermal equilibrium with this part, so these and these must be in equilibrium with one another. So if you remove this wall, at that condition, there will be no further flow of heat between A and B. Is it clear?
Yes, sir.
So we can say if two thermodynamical systems, let's say A and B, is individually in thermal equilibrium with third system C, then they must be in thermal equilibrium with one another. Krishna, is it clear?
Yes, sir.
Gautam, any doubt?
No, sir.
So we can say when two thermodynamical system is in thermal equilibrium, with third system then they must be in equilibrium with one another. It means if A and C is in thermal equilibrium, B and C is in thermal equilibrium, then A must be in thermal equilibrium with B. So in this whole part, we can say temperature is the physical quantity which should be responsible for the exchange of heat between any two thermodynamical system till they acquire equal temperature. Is it clear?
Yes, sir.
Yes, sir.
Mazia, any doubt?
No, sir.
What is written
Okay.
next to A?
A, that is temperature of A.
No, not the name. The name of the A part.
This part, this one,
Yes, sir.
adiabatic.
Okay. Thank you.
So temperature is the physical quantity which is responsible for exchange of heat between two thermodynamical system. Okay, just write it down.
Done, sir.
Done, sir.
Nabila, done?
Yes, sir.
Okay. Next is first law of thermodynamics. It's simply based on conservation of energy. Suppose you have a vessel enclosing any gas So in first part, if heat is given to this particular system, so this heat supplied to this system must be utilized in two different processes. First, to change the internal energy of the system, and there will be some work done on this piston to expand it from some initial volume to some final volume to move at this point. Similarly, if you have to eject some amount of heat from the system, so it should be provided by compressing this piston from some initial volume to some final volume and by decreasing its internal energy. So we can say in this whole part, the amount of heat ejected out or supplied to this particular system must be utilized in two different processes. One, the change in internal energy, and the second, the amount of work to expand or contract it. Is it clear?
Yes, sir.
Yes,
So
sir.
is this an ideal gas?
Yeah, we are just dealing all things in ideal gas. So we can say the amount of heat ejected out or supplied to the system must be utilized in changing internal energy as well as doing work. So dq must equals to du plus dw. dq is heat supplied or ejected, du is change in internal energy, and dw is work done. So dq is heat, du is change in internal energy, and dw is work done. Okay, just write it down. Done?
Yes, sir. Done.
Now we have three different parts. One is heat, second is internal energy, and third is work done. So we may divide these three different physical quantity into two parts depending upon their behavior. First is called state function. Those physical quantity which depends only on initial and final state of gas. It will be independent of path followed by the gas are termed as state function, such as internal energy, entropy. So state function is the physical quantity which depends upon initial and final point only, independent of path followed, is called state function. So first part, internal energy. So to calculate internal energy, it will be equals to N, number of moles, times R, universal gas constant, times dt, change in temperature, divided by gamma minus 1. Gamma is a specific gas ratio. It will be also equals to P initial V initial minus P final V final divided by gamma minus 1. In terms of degree of freedom, you may use half into degree of freedom, number of moles times R into change in temperature dt. Is it clear? So these are formula how to calculate change in internal energy related to the given condition in the question. Next is, suppose, yes,
So what is the last formula?
half F. F is degree of freedom, N is number of moles, R is universal gas constant, and dt is change in temperature. I've just transformed this gamma in terms of degree of freedom. Okay. According to the relation, gamma equals to 1 plus 2 by F. So move this 1 to left side. So you'll get gamma minus 1 is 2 by F. So it will become F by 2. Okay. Suppose there is a graph between pressure and volume for a gas in going three different processes. Along this way, path first, along this way, path second, and along this way, path third, from some point A to point B. So you're asked calculate change in internal energy along path 1, along path 2, and along path 3. Nabila, try to answer. What would be the relation between these three different change in internal energy related to this graph? Try to check whether the initial point and final point of all these are same or not.
Yes, it is the same.
So if you have to calculate difference between those 2 points, so is the difference of both these 2 points for all of the path will be same or different?
It would be same.
Good. So change in internal energy for all these three different paths must be equal to one another. Is it clear?
Yes, sir.
Yes, sir.
Gautam, any doubt?
So how did we get these formulas?
Which one?
The three formulas.
Okay. This one, this one, this one. I will define you later according to different processes. Just remember here how to calculate change in internal energy if you have related term according to the given equation. You may write this first formula if number of moles are change in temperature will be given and gamma will be given. Use this formula if there will be given term in terms of pressure and volume. You may use this formula if degree of freedom is given. I will define you later how we have calculated this or how we have derived this according to different processes. Okay.
Yes, sir.
Suppose this is pressure versus volume in which gas is going along this way. So what will be the value of change in internal energy for this path? Raza,
So can you repeat the question?
what will be the value of change in internal energy for this closed path curve?
0.
Good. So we can say change in internal energy for any closed path will be always 0. Since initial point and final point will be same, so difference of these two terms must be 0. Yusra, any doubt?
No, sir.
Okay, just write it down.
So what is the symbol you have used for integration? The circle in the middle.
If sign is like this, it means you have to simply integrate.
Yes, sir.
And if there is some closed path at this point, it will be integration over closed path. It means initial point and final point will be same. It is termed as closed integral. Or integration over closed path. You will have done?
Done, sir.
Yes, sir.
Next is path function. Those physical quantity which depends upon path followed by the gas are termed as path function, such as heat, work done. The physical quantity which depends upon path followed by gas. So first is heat. To calculate heat, dq equals to number of moles times molar specific constant C times change in temperature. This molar specific constant will depend upon process and may have different value according to different processes. So according to process, we are able to solve this dq and nothing special formula related to this. Or you may find according to first law. Next is the most important, work done. Work done is equals to force times displacement. You may write force in terms of pressure as pressure into area of cross section times displacement. Area times displacement will be termed as volume. So you may write P into dV integration to get total amount of work done. This is nothing but product of these two quantity. So in terms of graph, it will be defined by area. So we can say area under pressure volume graph will define you work done related to that process. Is it clear?
Yes, sir.
Yes, sir.
What was the justification for heat being path function?
It may depend upon path followed by the gas. For different path, it will have different value since it will behave as different process. Okay.
Yes, sir. But why did you write the formula for dq?
dq is heat supplied or ejected. It depends upon three parts: number of moles, molar specific constant, and dt. As we have defined in last chapter about specific heat, mass S delta T. So in terms of mass, here we use number of moles. In terms of specific heat, we use molar specific heat times change in temperature. Gautam, is it clear?
So C is the molar specific heat capacity.
Yeah.
Okay. But how is it show? How is this formula showing that it depends upon the path followed by the gas?
I will define you according to the process. Okay.
Okay, sir.
So if you have to calculate work done, let me define you. Suppose in a vessel, position of piston initially is at this point. Like this. So its initial volume will be at this point. If there is work done from inside, particle of gas on this piston to increase its dimension from this point to this point. So it will be initial volume and it will be some final volume. So if you plot pressure versus volume for this process. Let's say initial stated at this point. So on increasing volume, there may be change in pressure or there may not be. I'm just considering there is change in pressure by any process to this point. So graph will be along this way. So if you draw a perpendicular to this point, so it will define you volume initial, it will define you volume final. So if you further move this particular direction of curve, so it will go along this way, this way, this way to form complete circle. So the graph will be in terms of clockwise direction. Is it clear?
Yes, sir.
Yes, sir.
So in this part, since piston is going up, so volume of this whole system is increasing. So we can say final volume is greater than initial volume. So difference of volume in this part will be positive. It means work done in this case will be positive. Next, work done is positive, and this particular work done is done by the system of gas on piston to expand it. So we can say work is done by the system. Next, during this work done, there is some expansion of system. So we can say expansion of gas. Next, just take the direction of graph. So in this case, graph will be clockwise direction. Any doubt related to this part?
No, sir.
Raza?
No, sir.
Okay. Suppose gas is initially at this point. So initial volume will be VI. On compressing it from outside, there will be decrease in volume to this point. So let's say this is pressure and this is volume. So initially gas will be at this point. So on compressing it, there will be change in volume as well as pressure to reach at this point. So graph will be along this direction. So just draw a vertical line and extend this particular direction. So it will go along this way. This notation will be in terms of anti-clockwise direction. This will be initial volume and this will be final volume. So let me define you. In this part, final volume is decreasing as compared to its initial volume. So change in volume will be negative. So work done in this case will be negative. And in this part, work is done on the system by any external agency to compressing it. So we can say work is done on the system. In this part, gas is compressing. And graph related to this process is in anti-clockwise direction. Minashi, any doubt?
No, sir.
Okay, just write it down.
So can you scroll up?
This part?
The path function.
I'm just giving you just 5-minute break, okay? Just write it down. Okay. Any doubt related to this part?
No, sir.
No, sir.
For the above part, for internal energy and heat, let me define you sign convention. If temperature of system is increasing, change in internal energy will be positive. Temperature of system decreasing, so change in internal energy will be negative. For heat, if supplied to system, dq will be positive, and if it is ejected out, dq will be negative. Now, let me give you a question related to this part. Pressure versus volume. Initial point is at this point, V0. Final point is at this point, 2 V0. P0, 2 P0. And the graph is in this direction. So from this graph, try to find first work done, heat supplied or ejected, change in internal energy. Try to find. First, let me give you some hint. Gautam, how to calculate area of this particular curve?
What are the circle area formula? Go there. No.
Pi r square.
Yes, sir, that one.
Okay. So which radius you will use? Along x-axis or along y-axis?
Both are same.
No, both are not same.
Circle, right?
In this part, both are not same. Along x-axis, we have volume, and along y-axis, we have pressure. So how these two terms are seen?
But the difference will be same, judging by the figure.
Okay. It is in their own magnitude, or it's in their own unit. Let's say we are calculating in terms of volume, it will be 2 V0 minus V0. So it will be defined in terms of volume. So if you calculate 2 P0 minus P0, it will give you pressure difference. So this difference and this difference must not be equal to one another. So how do we calculate the area of this particular curve? Just remember, in whole physics, for any curve, let's say for circle or ellipse, we use area is equals to pi r1 into r2. not pi r square. R1 will be along x coordinate and R2 will be along y axis. Is it clear?
Yes, sir.
Gautam, any doubt?
No, sir. But will the answer be accurate?
Yeah.
Won't some part be left out if you do this? Extra or left out? Because they both are different, you said.
For any curve figure, we just use this area, okay, for case of ellipse or for case of circle. Let's say if you have any elliptical path, it will be in terms of like this. So for this part, this will be termed as length of major axis, and this will be termed as length of minor axis. So area related to this part will be pi a times b. Is it clear?
Yes, sir.
So in general, we use this formula for curve and physics. All of you just find work done and send your answer. Gautam, where is pi? And also check the sign of this particular expression. Minashi, any problem while solving?
So for work done, we should find the curve, right?
Yeah, work done is area under this curve. Since this is any curve for which R1 will be V2 minus V1 divided by 2, so it will be just V0 by 2. R2 will be 2P0 minus P0 divided by 2, so it will be P0 by 2. So work done equals to area under this graph, so it will be pi R1 into R2, so P0 by 2, V0 by 2 divided by 4. Is it clear?
Yes.
Yusra,
Yes, sir.
what will be sign of this particular work done? Positive or negative related to this particular curve?
Negative.
Good. Since this particular curve is in anti-clockwise direction, so for anti-clockwise, work done should be negative.
Negative.
It means gas is compressing. So the next part, what will be heat supplied or ejected related to this process? So just use first law. dq equals to du plus dw. What will the value of change in internal energy for this process? Minashi,
Yes, sir.
what will be the value of change in internal energy for this process?
0.
Good. So amount of work must be equals to heat supplied or ejected. So dq will be equals to work done, which is in minus pi p naught v naught divided by 4. This minus sign will define you heat is being ejected out from the system. Is it clear? Gautam, any doubt? Mazia? Okay, you all are done? Nabila, any doubt?
So could you explain again, please, from the dq is equal to du plus dw part?
Okay. According to first law, dq, amount of heat, change in internal energy plus work done. Since this particular process is in closed path, so for any closed process, change in internal energy will be 0. That's why I put the value of change in internal energy for this process to be 0. So what you left with dq and in right side dw. It means total work done must equal to heat. Is it clear?
Yes, sir. Thank you.
So amount of work done is in negative sign. So dq will be in negative pi p0 by 4. This negative sign in terms of heat will define you heat is being ejected out from this particular system.
Okay, sir.
Okay. along path ABC, heat supplied is 100 joule and work done on the system is 20 joule. For path ADC, work done by the system is 10 joule. Find heat supplied along this. Let me give you a hint how to solve this part.
Sir,
Just, yes,
sir, didn't the last question have a third part?
yes, Gautam.
Didn't the last question also have a third part? Or change in internal energy? Fine, fine, okay.
In this part, we have whole closed path like this. In this part, gas is going from point A to point C, one along this way, and in the other part along this way. So you can say for both these two parts, initial point and final point is same. So change in internal energy for first part, that is along ABC, must equals to change in internal energy for second part, that is for ADC. So calculate change in internal energy for both these two processes and just equate them to find the required value. Okay, Krishna?
So could you explain that again, sir?
Since in this process, in first part, gas is going along this way, A to B and then to C. For the second part, it is going along this way, A to D and then to C. So both these two processes having same initial point and same final point. So you'll say internal energy for both these two parts will be same since it having same initial and final point. Is it clear?
Yes, sir.
So try to calculate term in terms of internal energy and then equate them to find the required value. Keep in mind the sign convention related to each part. And first, we have heat supplied to the system, 100 joule, and work done on the system is 20 joule. For the second part, work done by the system is 10 joule. So we have to calculate the required part. Gautam, just check your calculation. Just write first law for A, B, C. dq equals to du plus dw. Put the value which is given according to the question. Then simplify du from this part. Again, for path ADC, dq equals to du plus dw. Put the value which is given according to the question. Then solve for du. And then equate these two, exchange internal energy, and then you'll get the required part. Use sign convention. dq is supplied to the system. It will be positive. If it is being ejected out, it will be negative. In case of work done by the system, it will be positive. Done on the system, it will be negative. Gautam, check your calculation. Raza, check the sign of work done. Gautam, your answer is correct. Good, Krishna. Minashi, check your sign. Nabila, just tell me what you'll say about this heat supplied to the system. It will be positive or negative?
It will be positive.
Good. So it will be 100 equals to change in internal energy. And what about this work done on the system?
Negative.
Good. So if you move this negative sign to left side, what you'll get for change in internal
100
energy?
plus 20 is equal to 120 is equal to du.
Good. Now put this value in the second part. So we have du is equals to 120. And what will be work done? Positive or negative?
Positive.
Good. So in total, you'll get 130 joule. Minashi, is it clear?
Yes, sir.
Raza, any doubt?
No, sir.
You all have done?
Yes, sir.
Yes, sir.
Mazia? Okay. Next is thermodynamical process. First is isobaric. The process which is carried out, iso means same, bar defines you for pressure. It means at constant pressure. So it will be also termed as Charles' law. The process which is carried out at constant pressure is termed as isobaric process. So P will be constant. According to ideal gas equation, PV is equals to nRT. So if P is constant, volume and temperature should be directly proportional to each other. So we can write volume proportional to temperature. Move this temperature to left side. So you'll get V1 divided by T1 equals to V2 divided by T2. It will be termed as equation of state. According to generalized formula, Pv to the power x is equals to constant. So what will be the value of x so that P becomes constant? So we'll say x will be 0. So related to this part, x will be 0. Put this value of x in the above expression for molar specific heat for this process. Molar specific heat at constant pressure. So it will be Cp equals to R by gamma minus 1 minus R by x minus 1, and x we have 0, minus 1, minus minus cancel out. So on solving, you will get gamma times R divided by gamma minus 1. If you change this particular expression in terms of degree of freedom, you will get 1 plus F by 2 times R. Gautam, is it clear?
So I think I did not get it.
Which part?
So from equation of state.
Okay. According to ideal gas equation, we have PV is equals to nRT. Okay. So if P is constant, so V must be directly proportional to temperature. since number of moles and R ideal gas equation or universal gas constant, so it will be constant. So you're left with this volume and temperature, and these two should be directly proportional to each other. Is it clear?
Yes, sir.
Now move this temperature to left side and pressure to right side. So you will get V divided by T equals to nRT divided by P.
Yes, sir.
So in right side, you will have some constant value. V divided by T equals to nR divided by P. This term will be constant. So if you put the subscript to be 1 and 1, you'll get same value. If you change its subscript to 2 and 2, you'll get same value since pressure is constant and number of moles and universal gas constant is constant. That's why I've written V1 upon T1 equals to V2 upon T2. Is it clear?
Yes, sir. But why is X 0?
Now I have just compared this relation for this generalized equation to get molar specific constant. So general equation of state for any process is PV to the power X is equals to constant. So if you compare this part with this one, so if you have to get P to be constant, so this particular term must get vanished. So what should be the value of X for with this particular term will get cancelled out.
0.
So you'll say X must be 0. Okay.
Yes, sir.
Now put this value of X to the generalized equation of molar specific heat constant. C equals to R by gamma minus 1 minus R by X minus 1. So we have X as 0. So I've just put the value of X to be 0 and solve it. You'll get this part. Now, if you further simplify this gamma in terms of degree of freedom, you'll get this expression. Is it clear now?
Yes, sir.
Nabila, any doubt?
No, sir.
Okay. Now, related to every process, we have to draw graph. And the graph and this thermodynamic, yes,
So the CP formula, did you give it last class?
yes.
Okay, that's right. Okay. Even the degree of formula, for degree of freedom formula, you gave it last class, right?
Just see here.
Oh, okay, sir. Got it.
Generalized formula for C
Hmm.
and general equation for PV is equals to PV to the power X is equals to constant for any gas.
Okay, sir.
All of you just write it down. You all are done?
Yes, sir. Done.
Krishna, done?
Yes, sir. Done.
Okay. Just to stop here for today, I'm just breaking you all in different breakout room to take Viva. Okay.